Good morning, students. Today in the syllabus of class 9 physics, in the chapter motion, we will be discussing the topic equations of uniformly accelerated motion. Today we will be deriving these equations by graphical method. Now before we discuss the actual method of deriving these equations, we need to know what are the equations of motion. So there are in total 3 equations of motion. The first is called velocity time relation. So velocity time relation is v equal u plus a t. The second one, it is called position time relation, and this one is given by the equation s equals, S stands for distance, displacement or position, ut plus half at square. The third one, this one is called position velocity relation. The equation is written as v square equals u square plus 2as. So we get 3 equations of motion: velocity time relation, v equals u plus at. Now v represents final velocity, u is initial velocity, is acceleration, t is time. Second, position time relation, s as I told you, distance, u initial velocity, t is time, and a is acceleration. So ut plus half at square. Similarly, the third one, position velocity relation, v square equals u square plus 2as, where v is final velocity, u is initial velocity, a is acceleration, and s is distance traveled, displacement, or the position at that particular instant. So now let's begin by deriving these equations one by one. Now as this is a graphical method, so obviously the first step that we need to do is to draw the graph. Draw the graph that is going to represent uniformly accelerated motion. So let's begin by doing the graph part. So this is the graph, velocity versus time graph for uniformly accelerated motion. Now you can see that on the y-axis I have plotted velocity, and on the x-axis there is time, and the graph looks like this. This graph has been drawn for the condition initial velocity not equal to 0. Uniformly accelerated motion when initial velocity is not equal to 0. So the graph doesn't begin from origin. It begins from a point A that shows the value of initial velocity, and then the graph goes up to B, which represents the position for final velocity V. Okay, so initial velocity and final velocities are u and v respectively. So the velocity has been pointed, and at time 0 velocity is u, and at time t velocity is v. That is the final velocity. Okay, so this is how the graph is going to look like, and this graph will be used in deriving the equations of motion. Now let's point out a couple more information on this graph. Now as u is the initial velocity, so OA should be equal to u. OA should be equal to u. Now as OACD is a rectangle and opposite sides of a rectangle are equal. So OA should be equal to CD. So if OA is equal to U, then CD should also be equal to U. So let's mark CD as U. Now final velocity corresponds to point B. So obviously BD should be equal to V. The value BD should be equal to. So let's mark BD equal to V. Okay. So now BD is equal to V. BD is V, CD is U, then BC. How to find out BC? BC should be equal to BD minus CD, isn't it? BD minus CD. So BD is V and CD is U, so BC should be V minus U. BC is equal to V minus U. This is the length V minus U. Now again coming back to the x-axis part, OD corresponding to D, the value of time is T, so OD should be equal to T. OD should be equal to T. Again, since OACD is a rectangle, so OD should be equal to AC. Opposite sides of a rectangle are equal, so OD should be equal to AC. So let's mark AC also equal to be T. So this is going to be the graph and the value to be used for deriving the equations of motion. So we have plotted all the values and we'll be using these in deriving the equations one by one. So let's start with the first equation of motion, is the velocity time relation V equal to U plus AT. So we'll be deriving this equation first of all. So using the graph, we know that acceleration is equal to slope of the velocity time graph. Slope of the velocity versus time graph. Acceleration is slope of the velocity time graph. Now slope. For calculating slope, we have to consider a right angle triangle. So the right angle triangle is ABC. You can see in the graph ABC. That is the right angle triangle. So slope is given by perpendicular by base. Perpendicular by base. So perpendicular is BC and base is AC. Perpendicular BC and base is AC. So in this manner we can find out the slope. So in the right angle triangle ABC, perpendicular BC was equal to BD minus CD. Now this thing we had already done. BC we had already solved for it. Still, let's do it again. So BC is equal to BD minus CD. BD is equal to V and CD is equal to U, so BC will be equal to V minus U. That we have already seen in the graph. Now the base AC is equal to OD. C is equal to OD, so that should be equal to T. So now we can substitute the values. So therefore slope is equal to BC divided by AC, and that is equal to V minus U divided by T. Now as acceleration is equal to slope, that is V minus U by T. Acceleration is given by the alphabet A, symbolized by A. So let's write down the equation as A equal to V minus U by T. This is the equation that we obtain after substituting the value of slope. Now let's take T to the other side of the equation. That will give us V minus U equal to 80. Now if we take U to the other side of the equation, then the minus sign will change to plus. So V is equal to U plus 80. So this is the first equation of motion, which is called the velocity time relation. So we have derived the velocity with time relation V equal to U plus 80 by the graphical method. We can move ahead and start deriving the second equation as equal to ut plus half at square, which is the position time relation using the same graph. Now as distance is equal to area under the velocity time graph. Now in place of distance you can also write down displacement. So it could be the total distance traveled or the displacement of the object, that is given by area under the velocity time graph. Now from the graph you can understand that the area enclosed under the graph is that of a trapezium. The geometrical shape is that of a trapezium OABD. OABD is a trapezium. So we have to find out the area of this trapezium to find out the distance or displacement. So therefore, distance or displacement is equal to area of the trapezium OABD. Area of the trapezium OABD. Now area of a trapezium is given by the formula half into sum of parallel sides into height. Now in this diagram, what are the two parallel sides? So the parallel sides are OA and BD. OA and BD are the parallel sides and the height is OD. So OA and BD are the parallel sides and OD is the height. So let's substitute the values and write down the formula. So area will be equal to half into sum of the parallel sides multiplied by height. So that will be equal to half into OA plus BD multiplied by OD. Half into OA plus BD into OD. Now OA. OA is equal to U and BD is equal to V. OA and BD, and then OD is equal to T. Let's write down S for distance. So S is equal to half into U plus V into T. So this equation is obtained after substituting the values. From first equation of motion, we have already derived the first equation of motion, V equal to U plus AT. We will substitute the value of V in this equation. So S will be equal to half into U plus, now in place of V we will write down U plus 18. Now let's change the bracket to a square bracket. So this will give you U plus, now you can open one bracket and write down instead of V U plus 18. Close the bracket, multiplied by time. So S will be equal to half into U plus AT and then multiplied by time. Now you can add down the two terms of U, so that will give you S equal to half into twice of U plus AT multiplied by T. So the next step that we need to do is to multiply both the terms by T. That will give you, the first term will be twice UT plus AT square. So now taking out both the terms from the bracket, you will get twice UT by 2, since half has been multiplied to both the terms. So twice UT by 2 plus AT square by 2. Cancel out 2 in the first term. So now we are left out therefore with S equal to UT plus half AT square. So this is the final equation, the second equation of motion, that is called the position time relation. Position time relation. So this is the proof for the second equation of motion, is equal to ut plus half t square, position time relation. Now the last one, position velocity relation, v square equal to u square plus 2as. So the same graph will again help us to derive this equation. For this equation again we are going to find out the area under the graph. This means area of the trapezium OABD. So area under the graph gives distance or displacement. So we will follow the same step to begin the proof. Distance or displacement is area under the velocity time graph. Therefore distance is area of the trapezium OABD. And we know that area of trapezium is given by half into sum of the parallel sides into height. Parallel sides are OA and BD and height is OD, so S will be equal to half into OA plus BD multiplied by OD. Substituting the values, you get S equal to half into U plus V into T. Now this much we had already done for the second equation also. Proceeding thereafter, as v is equal to u plus at. This is obtained from the first equation of motion. So therefore v minus u is equal to at, which implies t is equal to v minus u by a. Okay. So now we will substitute the value of t in the expression for s. Half into u plus v into t. In place of t we will write down v minus u by a. So let's substitute the value. On substituting we get therefore s equal to half into u plus v into, in place of t we will write v minus u by a. Let's enclose this term inside a bracket. So s is equal to half into u plus v into v minus u by a. Now u plus v is same as v plus u. So you can write down s equal to half into v plus u into v minus u divided by a. Now check the numerator part. V plus u multiplied by v minus u. Doesn't it remind you of an identity? Using the same identity, multiplying the denominator, that gives you 2a, and v plus u into v minus u. You will get v square minus u square. Can you recollect which identity is used here? Since a plus b into a minus b is equal to a square minus b square. So we have used this identity. In place of a it is v and in place of b it is u. So s is equal to 1 by 2a v square minus u square. Taking 2a to the other side of the equation, we get v square minus u square equal to 2as. Now if u square is taken to the other side, this negative sign will change to a plus sign. So v square equal to u square plus 2as. So we finally obtain the third equation of motion, which is called position velocity relation. V square equal to u square plus 2as, position velocity relation. So let's quickly remember the three equations: v equal to u plus at, s equal to ut plus half at square, and v square equal to u square plus 2as. So using this graph we have obtained the three equations for